Hey, this is the second half of Lecture 19. We are looking at sections 5.1 and 5.2 on maxes and mins and concavity and things like that. So we are jumping in here in the middle, and we're going to look at the concavity of a graph at various points. Now, before I get into that, let's talk about what concavity is. If I think about 2 points, I can connect these 2 points in a lot of different ways. One way is that I could create the straight line between the two of them. That has no concavity. It is straight. It's not concave up, nor is it concave down. If I were to connect these with a curve such that it is arched downward, it would look like this. Okay, now how arched you want to make it is up to you, but in that case, this is concave down. Right? It's almost like a sad face. And the other half, we could also connect them such that it curves out this way. In that case, this is concave up, more like a smiley face. Okay, now how far and how wide that concavity is not super important. We just need to know which way is it. Is it curved downward? Is it curved upward? Okay, so that's for reference as we move forward. So this time, let's take a look at another graph. And again, I'm going to give you a little plot here. Let me see if I can do something straight. And let's say that I've got a point here at x equals 0. And then let's go to a point up here at 2. And let's make it symmetric. So we'll go over here to -2 and put a point down here. And we're going to connect this. So this is going to go up like this. And this is going to go up like this. And then it's going to change curvature and go that way. And then this one's going to come down this way. Okay. And what we want to do here is we want to analyze the concavity. Okay. So first thing I want to do is talk about the point there in the middle. So this point right here is what I'm going to call an inflection point. That's where the curvature changes, right? Because to the left of that, you have something that is curved up. Right? It's happy face. So that one would be concave up. And it's concave up on the interval from -infinity to 0. And to the right of that red point, we have sad face, curved downward. And so that one we would say is concave down. And it's concave down on the interval from 0 to infinity. And my red point is what I'm calling an inflection point. And that's where the concavity changes, and that's at x equals 0. Okay. Now what we want to be able to do is to connect this behavior to our derivatives. So let's look at our tangent lines. So if I think about drawing in a bunch of slopes of tangent lines here, let me pick a fun color. Let's go with this one. All right, so on this blue line, let's draw in some tangent lines. Now, the first thing you may notice is that they don't all point down and they don't all point up. You've got some up and some down. So the positive-negative relationship that we had from the first derivative and the increasing-decreasing is not going to be the same for concavity. But what I want you to think about is that my slopes on the far left are pretty steeply downward. They're going to be really negative. And slowly they become less steep as I hit that middle point, that minimum at the bottom, where it becomes 0. And then notice they become positive. They start going up, right? So I go from being steep down to more plateaued to steep up, which means that my slopes are increasing. Okay, so if my slopes are increasing while I'm concave up, so slopes increase. Slopes represent your first derivative. And if your slopes are increasing, that's going to tell you that your second derivative is positive. Right? So in the last year, we said that if the derivative was positive, or our slopes were positive, then the function was increasing. Now, if the slopes are increasing and that's the first derivative, then the derivative of that must be positive. So that same kind of relationship works here as well. The same thing's going to happen when we're concave down. So take a quick peek at this. We start out positive, a little less positive, 0, and then we start hitting negative pretty hard. And it goes steeply negative. So these are decreasing. So our slopes, which are our first derivative, are decreasing. And when our slopes decrease, the derivative of that, which is the second derivative, are going to be negative. And you might imagine that for an inflection point, our second derivative is going to be 0. Okay, so these are the relationships that we get. And I'm actually going to move this to the side so I don't mess up, oh shoot, my graph or where I need to write things down below here. So let's move it to the side. There we go. Okay, and that allows us to fill in these things. So if the second derivative is positive on an interval, then the graph of the function is going to be concave up. If the second derivative is negative, then the graph of the function is concave down. And if the second derivative is equal to 0, then at that point, that point is what we're going to call a possible inflection point. Just like we said, our max and mins, we weren't sure. Same thing happens for our inflection points. It's possible until I prove that it is. Okay. Now, keep in mind here, at our local max, up top here in the green, it's concave down. Right? So at a local max, f of x is concave down. And a local min, down here at the bottom, is where that is concave up. And we're going to use that to be able to determine when our points are maxes or mins. And that's going to lead us right in to the second derivative test. So we're going to use this information to test our points. So again, second derivative test does the same thing the first derivative test does. Instead, it uses the second derivative to determine whether a critical point is a local max, local min, or neither. So here's what we need to do. Again, first step is to find the critical points. Then last time we had to set up intervals and pick other points and test things all over the place. Don't have to do that here. We get to cut to the chase and just test those critical points. We're going to test them in the second derivative because it's the second derivative test. And then we're going to use what we know to determine whether it's a local max, a local min, or neither. Now, I gave you some information here, but for me, again, I write down some visuals that help me make a decision. So let's take a look at this one. All right, so first thing we need to do is get our critical points. So in order to find critical points, we take our first derivative. If you're not taking derivatives, you're definitely not doing it right. Derivative here is going to be negative 2x squared plus 7x minus 3. And we're going to set that equal to 0 to get our critical point. So our critical point is where that is equal to 0. Now I'm going to multiply it through by negative. So that gives me 2x squared minus 7x plus 3. Now I'm going to try to factor this. When I factor this with a number in the front position there, I'm going to use my box and circle. So my 2x squared goes here and my 3 in the bottom. And I multiply those two, and that gives me 6x squared. Now, two factors of what's in the circle that add to negative 7. So negative 6 and negative 1 will do it, but they both need an x to go in that position. And then I'm factoring the box. So if I look at the first column, they both have a 2 and an x. So I'm going to pull out a 2x. When I do that, if I take 2x out of 2x squared, I have an x left over. If I take the 2x out of negative 6x, I have a negative 3 left over. And if we do it the other direction, if you take an x out of the negative 1x, you should have a negative 1 left over. And then you can check that negative 1 times negative 3 is the positive 3 that's in that box. When you do that, then this and this become your two factors. So that means that I can factor this as 2x minus 1 and x minus 3. Now, if you don't like that, you can go quadratic formula on this one, and you'll be able to find your answers that way just as easily. If you set both of these equal to 0, this becomes x equals 1/2, and this becomes x equals 3. If you need to take a second and find those, feel free to do that. And so this time I have 2 critical points. Now, if I were using first derivative test, I'd have to set up the domain, which in this case is all real numbers because it's a polynomial, and I'd have to break it up at both of those 2 spots and get 3 different test points and test 3 different things and go through the whole process. Don't have to do that with second derivative test. What I do have to do is calculate the second derivative. So the first derivative is at the top of the screen there. So the second derivative then is going to be negative 4x plus 7. Okay. And again, I don't need test points. I'm going to actually test my critical points. Now, the reason we didn't test our critical points in the first derivative test is because if you plug those into the first derivative, they're going to give you 0, right? And that's not positive or negative, so it doesn't give you information that you can use. Here, I won't get 0 most of the time, and so I can figure out what's going on. So I want to test both my critical points. So x equals 1/2. If I plug that in, and again, I don't need the number. I only need the sign of the number. So if I take negative 4 times 1/2, that's negative 2. Plus 7 is going to give me positive 5, but I really only care that it's positive. If the second derivative is positive, it tells me that this is concave up. And when the curve is concave up, then my critical point has to be here at the bottom, which means this one has to be a local min at x equals 1/2. Then I'm going to test the second critical point. So if I take x equals 3 and I plug that one in, negative 4 times 3 plus 7, I'm going to get negative 12 plus 7, and I'm going to get a negative answer. In that case, it's concave down, and I must have a local max there at the top. So we have a local max at x equals 3. And using the second derivative test, I'm able to classify my extrema. I can find my maxes and mins. Okay. Now, if you happen to get 0, your second derivative test fails, and you got to go back to first derivative test. Okay, it doesn't tell you anything. But that's how we find our local maxes and local mins. Now, benefits to using one over the other, right? So second derivative test requires you to take a second derivative. So if your first derivative was messy, then maybe you don't want to take a second derivative, right? First derivative test will always work. Second derivative test can fail. But in a lot of cases where the derivative's quick and easy or quick and straightforward, second derivative test is a lot quicker. So totally up to you on what you want to use. All right, and then the last thing that we want to do is we want to be able to find inflection points and intervals of concavity. So we are going to take, is this the same function? It is. We're going to take the same function, and we've already done some work up above. So what do we know about this? We know that the first derivative first derivative, not second. We know that the first derivative is negative 2x squared plus 7x minus 3. Ooh. There we go. And we know that when we set this equal to 0, this produced critical points, x equals 1/2 and x equals 3. We already did that. I'm not going to do it again, right? Okay. Then we also know the second derivative. Second derivative here. Whoa, why is this jumping around today? Sorry about that, friends. This is negative 4x plus 7. Now, my critical points came from the first derivative. If I do the same thing with the second derivative, it's going to give me possible inflection points. So in order to find my possible inflection points, which I call PIPs, we're setting the negative 4x plus 7 equal to 0. Subtract your 7, divide by 4, you get x equals 7/4, which is the same as 1 3/4, 1.75 if you don't like fractions, right? So this is my possible inflection point. If I want to figure out where the function is concave up, concave down, and if this is an inflection point or not, I'm going to do exactly what I did with the first derivative test. I'm going to think about the domain, which in this case is negative infinity to infinity because it's a polynomial, and I'm going to break it at my possible inflection point. So I'm going to split everything up at 1.75. So on the right, I'm going from 1.75 to infinity. On the left, I'm going from negative infinity to 1.75. And I'm going to choose test points just like first derivative test. I think 0 is in this one, and 2 is in this interval. And we're going to test them in the second derivative because I want to know about concavity. So we're plugging into the second derivative. That's going to tell me things about the original function. So if you plug in 0 for x, then you get positive 7. So that's positive, and that means it's concave up. When you plug in the 2, that's negative 8 plus 7. That's a negative number, and that means concave down. So now you can see that the concavity did change, and that makes this an inflection point. So not possible anymore, but this is actually an inflection point. So what do we know? We know that we have an inflection point at x equals 1.75. We know that it is concave up on the interval from negative infinity to 1.75, and I'm just reading from my chart where it has the smiley face. And we know that it is concave down on the interval from 1.75 to infinity, right? Just from the little chart there. So we can actually determine if we use the first derivative test ideas with the second derivative, it tells you about concave up, concave down, and inflection points. If you use the first derivative test type things with the first derivative test, it tells you increasing and decreasing and local maxes and local mins.